Okay, so we're going to move on to 11.3, which is our first official new test. This is the integral test. Now, remember that when we're dealing with infinite series, there's a relationship to improper integrals. I've already mentioned that before. So let's go ahead and look at this. Now, let's say, then this is y is equal to 1 over x. Let's say that I want to find the area from 1 to infinity of 1 over x dx. I need to determine whether that is convergent or not. So really what we're doing is we're looking for that area and trying to determine whether it is convergent or divergent. Okay? So when we're dealing with the sum from n is equal to 1 to infinity of 1 over n, here's the thing. We are actually, basically what this winds up being is basically the Riemann sum for that improper integral. Okay? And so what we have here is we need to since the width between them is 1, basically the value here, right here at 1, is the same as the area here, right? Because in order to get the area, all you have to do is multiply by 1. Okay, so that means that here, so what we wind up getting is we just wind up getting an infinite Riemann sum. And this is not only helpful in us understanding how the integral test can help us, how this relates to this. It's actually going to come back and benefit us even more later when we start talking about the error between them. Well, here's the thing. I actually really don't like this Riemann sum because it winds up being overage, right? So even if this winds up being convergent, does the overage basically mess us up, right? Because basically this is larger than this. So if this winds up being convergent, and of course we know this isn't, but if the one that we're actually dealing with is convergent, then the overage doesn't wind up telling me much. Well, here's the thing. Let's go ahead and redraw that, okay? And let's relate that. We know that this was the Riemann sum to the left. I mean, the left-hand Riemann sum. What is the relationship between the left-hand Riemann sum of this series and the right-hand Riemann sum starting at 0? Well, the only difference should be the fact that everything is just shifted over 1. Okay? So if it's just shifted over 1, and it's going off to infinity, that really shouldn't make a difference, right? Because basically this maps onto that, this maps onto that, this maps onto that. And so if everything just shifted over to the left one, we can still do an integral from 1 to infinity. We just have to actually calculate the area of this one. So the area of rectangle 1 plus the integral from 1 to infinity of f of x dx. Well, that's finite, and if that's convergent, then the sum is convergent. So that gives us a rationale behind why we can actually use the integral test. The integral test actually states that if the corresponding integral is convergent, then the series is convergent. If the corresponding integral is divergent, then it's divergent. So let's go ahead and let's look at an example. Let's say we have n is equal to 1 to infinity of 2 over 3n plus 5. Well, that is related to f of x is equal to 2 over 3x plus 5. Okay, well, let's go ahead and see what happens from 1 to infinity of 2 over 3x plus 5 dx. Well, I happen to know that I don't like that 2 out in front. I want to put a 3 there, so I need to pull the 2 out in front and divide by 3 when I put a 3 up in that numerator, plus 5 dx, and that actually winds up being 2/3 times natural log of 3x plus 5. Of course, I don't have to use the absolute value bars because I know it's going to be positive, but just force of habit, from 1 to infinity. But remember, when I'm doing an improper integral, I actually need to use limits. So it's actually 2/3 times the limit as b approaches infinity of the natural log of 3x plus 5 from 1 to b. Once I've done that, I know that it's 2/3 times the limit as b approaches infinity of the natural log of 3b plus 5 minus the natural log of what? Well, when I plug in 1, I'm actually going to get 8. Well, here's the thing. That's finite, but when b plugs into there, I don't care how slowly natural log actually approaches infinity. As its input approaches infinity, that approaches infinity. So that either does not exist or approaches positive infinity, however you want to deem it. But either way, that gives us the conclusion that this integral is divergent, and if the corresponding integral is divergent, then the sigma, the series, is as well. Okay, divergent. Okay. Now, you're like, well, that actually looks awfully familiar, and I noticed that was first degree right here, and I remember something about the degree mattering when we were dealing with improper integrals. And you'd be right, okay? When we're dealing with improper integrals, remember that we had, from 1 to infinity, or whatever constant it is, 1 over x to the p dx, okay? And as long as p was greater than 1, it converged, okay? And as long as p was less than or equal to 1, it diverged, okay? Well, the same thing is going to happen here with the, make sure it's positive, right? It's got to be positive, otherwise it pops back up into the numerator. It's obviously divergent at that point, but you get the idea. Well, we have the p-series rule, which basically is sort of an implication of having done the integral test a couple of times with sort of the same classification of series. So we have 1 over n to the p, and it winds up being the same sort of thing. If p is greater than 1, it converges. If p is less than or equal to 1, it diverges. Okay? And that's called the p-series test. And it's basically a corollary of the integral test. So the integral test basically says if the corresponding improper integral converges, then the series converges. If the corresponding improper integral diverges, then the series diverges. Very, very simple. Well, let's go through a couple more examples. We see, even if we're given it in this form rather than in sigma notation, we should be able to figure out whether this converges or diverges. Well, that means that its n is equal to, and I could start at 2 if I wanted to. It doesn't really matter. So let's start at 1, just for the sake of argument, since we're used to doing that. So it's the natural log of n plus 1 over n plus 1. Actually, you know what? It simplifies things just to go ahead and start it at 2, and you have natural log of n over n. Okay, well, if the corresponding 2 to infinity integral of natural log x over x dx, if that converges, then this converges. If it diverges, then it diverges. I have this funny feeling that it's going to diverge, right? And this, we'll actually get into this in the next section, but it's good to have that nice sort of hunch going in. I know that 1 over n is going to diverge. All natural log n does is make each term a little bit larger. So basically this right here, for the interval that we're dealing with, from the positive integers on out to infinity, this is always going to be larger than 1 over n, and if 1 over n already diverges, then it's going to diverge. So what's called a comparison test, and we'll get into that before long. Here, let's go ahead and just grind out and show analytically, using the integral test, that this does indeed diverge. Now remember that this is one of those tricky ones that is u sub in that form, so it's u du. But remember, again, this is improper integral, so I need to use the proper notation. I need to use limit. So at limit as b approaches infinity of 2 to b of natural log x to the first, 1 over x dx, and that's u du. So it winds up being the limit as b approaches infinity of 1/2 b squared from 2 to b, x squared. So the limit as b goes to infinity of 1/2 natural log b squared minus 1/2 natural log 2 squared. Well, this is a finite number right here. But again, as b goes to infinity, natural log b goes to infinity. It goes slower, but it still goes to infinity. And its squared just makes it a little bit more aggressive, so this actually goes to infinity. It diverges, and therefore the original sequence diverges by the integral test. Okay, and we're just going to keep going through a couple more examples and sort of, and this is a nice excuse not only to relate these back, since it's just kind of neat that these series wind up being functionally they wind up being infinite Riemann sums, and that's how they relate. Well, that means that you're actually going to be able to use the integral to get some sort of estimate, okay, of that series, especially like if you truncate it to a particular number of terms, that is. Okay, well, let's look at, I'm not number them, I'm not doing them out of your book, I'm sort of doing it from another book. So we have arctan of x, n over n squared plus 1. Well, that means that I need to evaluate the improper integral 1 to infinity of arctan x over x squared plus 1 dx. And this bears a striking resemblance to the last one that we did because it's that u sub again. So let's go ahead and put it in the limit notation. Let's go ahead and pull it apart into u du. That allows us to see it a little bit better, and we don't even have to actually do the integration. Do the u substitution in order to do the integration. So we go ahead and get 1/2 u squared from 1 to b. Limit as b approaches infinity of 1/2 arctan b squared minus 1/2 arctan 1 squared. Well, here's the thing. As b goes to infinity, nothing's going to happen to this. Arctan of 1 is pi over 4. Pi over 4 squared is pi squared over 16, and that winds up being basically pi squared over 32 as b goes to infinity. As b goes to infinity, that's a constant. It basically just is, right? As b goes to infinity, arctan, remember, winds up hugging the asymptote at pi over 2. Okay, well, if that's squared, then the asymptote is if the output is squared, then the asymptote is squared, and it winds up being pi squared over 4. Pi squared over 4 divided by 2 is pi squared over 8. Okay? And therefore this winds up being 3 pi squared over 32. That actually, as messy as it is, and as nasty of a approximation that's going to give us in our calculator, it is a finite recognizable number. So the improper integral that is related to our original series, it converges to a specific number, and therefore we happen to know that this converges. Now, it doesn't tell me the actual value for the series, it simply tells me that it converges. And that's kind of nice, okay? Let's do one more. Okay. Well, I don't really like the way that looks, so I'm going to actually change that into 1, 2 to the 2/3, 1 over 3 to the 2/3, 1 over 4 to the 2/3, and 1 over 5 to the 2/3. So really that is n is equal to 1 to infinity of 1 over n to the 2/3. Well, my p-series test told me what? That this exponent needs to be greater than 1 for this to converge. This does not converge, okay? This diverges by p-series, okay? Diverges by p-series because p is greater than, or p is less than or equal to 1, right? Remember, it's the same rule with respect to just simple expressions like this. It's the same rule that we had when we dealt with improper integrals of this variety. If that exponent is greater than 1, it converges. If it's between 0 and 1, it diverges. Okay. Well, I think that's a good starting point for our discussion of the integral test. We'll go ahead and do one more video on this. And towards the end of the video, I'll show you sort of how we can estimate error and a couple other things like that. And then from there, we will move on to 11.4, which is the comparison test, which actually has 2 different tests within it. But this sort of had 2 different tests in it as well, both the integral test and the corollary of that, the p-series test. So go ahead and email me with any questions that you might have, and I will go ahead and get started on that next video for you. Bye-bye.